Hey everyone, thanks for being here today at the TigerGraph Graph Deep Learning panel. The Graph Deep Learning space is seriously super exciting. So I'm sure the conversation with our panelists will be eye-opening. I'm the moderator for this panel. My name is Neil. I'm a lead research scientist at Snapchat, and my work largely focuses on academic and applied research in graph machine learning and graph neural networks. So we have an awesome lineup here today. Let me briefly introduce our panelists before we get started. Firstly, we have George Carapace, who is a senior principal scientist at AWS AI and ML and a distinguished Knight University professor at University of Minnesota. Next, we have Victor Lee, who's the vice president of machine learning at TigerGraph. Victor is, he received his PhD in computer science from Kent State University with a focus on graph data mining. And before TigerGraph, he was a visiting professor at John Carroll University. And finally, we have Vikram Munduru, who's a solutions architect at AWS, helping strategic ISV startup customers in the San Francisco Bay Area. And Vikram comes with a background of designing, implementing, and migrating solutions like DevOps, AI and machine learning, and software as a service on the AWS cloud. And just to give our audience a little bit of an idea about the structure of the panel, I'm going to ask a couple of thought-provoking questions to the floor and allow our panelists some time to think before jumping at the answers. So totally anticipate a couple moments of silence as our panelists gather our thoughts respond. Okay, so let's just get started. So since this is a graph deep learning panel, let me start by asking, what does everyone mean by graph learning? And how does it differ from most of what people talk about when they talk about machine learning?
Okay, let me take a crack at that question. So.
Go ahead, George. Yeah.
Okay. So Victor, you started first, man. Go ahead.
Oh, me? Okay. So I'd compared graph learning to, more traditional machine learning. So machine learning, you have a data set, a number of records, often tabular data, right? And what you're trying to find is, by studying that existing data, do you see some pattern so that you can make predictions about if I see another data item from the same sort of stream of data, can I make some sort of prediction about that? And the difference with a graph is that now you assume that there are connections, relationships between those data items, where previously you didn't necessarily have that in the training data. Maybe you were actually trying to make a prediction about the relationships, but now you're given some known relationships, and that actually becomes part of the identity of the data items. If a graph in some sense may have a life of its own, and you're trying to understand that organism. And so when you're doing graph deep learning, you necessarily must, but you also get to take advantage of those relationships in trying to make your predictive model. It potentially gives you a deeper understanding. So I'll leave it there and like to see how other people describe it.
No, this is very good. I think the relation is the key, right? And let me give you guys another example, right? That kind of that drives the point that Victor was making, right? So so in one of the simplest methods to do machine learning is to do what is called a nearest neighbor classifier, right? So in other words, my label, right, is that of the most nearest neighbor, most similar other object, right? From a particular data point, and I have a way of computing similarity between data points, and then I see which of the labeled data points is most similar to me, right? And I inherit each label, right, as a prediction, right? So in the context of a graph, right, when I have a graph that connects the data points with other data points via those explicit relations, right, then I don't have to go and find out which are my nearest neighbors. To a large extent, those nearest neighbors are given to me, right? So then I can use information from those neighbors, right, to be able to help me predict, my label. Right. So if it's I can look at all the other nodes that I'm connected to, right? And if it's a graph that connected to things of the same type, right? And out of the one that I'm connected to, I look at which of those things have labels, and then I can look at something as simple as like a majority rule, to actually do the classification, right? So in essence, really the key idea between graph machine learning and traditional machine learning is that I can take advantage of those relations to create and the priors that those relations impose to actually help me, compute it to perform the prediction, right? So.
Thanks, George. Yeah, I want to just follow up a little bit about graph neural networks. So I hear a lot of talk about graph neural networks these days and how they kind of fit within the space of graph machine learning. So I kind of just wanted to ask for a little bit of an overview about graph neural networks and some thoughts on how they compare to some of these prior art approaches that leverage structure in the graph. Do you think these kinds of models, these graph neural network models, will render kind of these traditional models obsolete in some sense?
Okay, so let me take a crack of giving a high-level overview of what a graph neural network is, and so usually in the context of graph learning, there are a couple of problems that I'm trying to solve, right? So probably the simplest problem I want to solve is what's called a node classification problem, right? So the goal over here is to build a model that's going to predict something about a particular node, right? And let's say for every node in the graph, right? So in the context of a graph neural network, the way graph neural networks work is they at a very high level, right? They define some sort of a receptive field right around that node, right? And the way they do that part is by creating a subgraph around that node, right? And usually the subgraph is parameterized. It's created in such a way so that will include all the nodes that they're up to k hops away from that node that I'm trying to classify. So usually we call those things like a k hop ego network, right? And then what a graph neural network does is learn a deep learning model, right? That takes into account the information from that ego network, right? In order to be able to solve the classification problem, the node classification problem, right? And of course, there are different mechanisms by which that information from that ego network is taken into account, right? And and those different ways of doing that, give rise to different types of graph neural network models, right? So the simplest one is to just, iteratively aggregate, the information from the neighbors, right? And do that thing, k times, and by doing k times, you pull information from neighbor that are up to k hops away, right? And the key part of a graph neural network is the way that information from the neighbors is aggregated, right? And is used to combine it with the information of the node itself. This is done via functions, but that they are learnable functions, right? And those are nonlinear and learnable functions. Okay, so what the model learns, it learns, how to aggregate that information, right? In order to compute a representation of the target node, right? So that representation, will allow me to have a very accurate classification model, right? So usually you take the representation and you fit it in some sort of an MLP layer, then you define a classification loss and you backpropagate, right? And that way you estimate the parameters of your GNN models, right? So, and again, the parameters is how the information from the neighbors are communicated and how they're combined, right, with the information of the node itself. Okay, so then at a high level, then if you think about, my prediction is a function of the information in my ego network, right? For the node classification task, right? Now, how that information is utilized and combined in order to give my representation is learned, as a result of, doing a backpropagation in a standard kind of, deep learning setting. Now, this is different for some of the more traditional ways of solving the node classification problem, right? So in a traditional graph learning, so let's say a simple way is to have some sort of an a priori determined mechanism by which information from the neighborhoods are combined, right? In order to be able to get a representation of a node in order to fit it into my downstream classifier, right? In order to come to classification, right? So there are no learnable parameters in terms of how the information from the neighborhood would be actually combined, right, in order to give a representation, right? So one of the key difference between a GNN versus some of the more traditional approaches, it has to do with the fact that the information is actually that the combination function is learned, right? And that combination function is can be an arbitrarily complex, deep neural network, right, in terms of how I combine them, right? And I think this is one, and and as a result of it's a complex neural network, it has the advantage of potentially doing kind of the multi-level feature engineering, right? So if you think about, the deep neural network that's able to learn, features at different level of abstractions, right? So this is what you achieve by using a GNN versus, some of the traditional approaches. And I'll let anybody else, to contribute to that.
I wanted to, for those people who maybe have less of a background in deep learning, data science in general, I encounter this issue often where I'm speaking to an audience and I don't know what their background is, so I try to touch on something for everyone. Maybe look at an example of you're trying to recommend products that people would buy. And so you have a set of customers, potential customers, you have a set of products, you have features of those products. So you've got maybe 3 types of nodes: people, products, and key features of products. And what do you have? What information do you have? And this is actually can be a very traditional machine learning problem. People have done this with they've done it in ways where they at least weren't thinking of it as a graph. You can make a graph very easily of relationships between what people purchased. There's a relationship between a product and a feature, and between people who have previously purchased a product and given it a strong rating. You call this, collaborative filtering and feature-based and recommendation. But you can formulate it as sort of a traditional matrix problem rather than a graph problem. Where it gets sort of an interesting graph spin is when maybe you look at the social network between people, and does a friendship between, like, do you trust the opinion of this person? Or if you see that these are complementary products, so you have a product to product relationship, and adding in those sorts of things adds additional information, which again could be solved in a more traditional way, but it's starting to lend itself to looking like a graph, looking like a network. And that's sort of where you can see, again, even if you don't really know how neural networks work or deep learning works, but you can see why predictions can be dependent on this sort of information. We've all heard the phrase, you just bought product X, you may be interested to know that other people who bought product X often bought product Y and liked that. And that's, a form of collaborative filtering. There's sort of a simple graph path of you to product X, to other people who bought X, to other products they bought. And then when you bring in the other dimensions of the social network or the product to product relationships, that can add in this sort of what George referred to as the K-hop ego network, or the sort of the surroundings around a particular thing in the graph. And that can add more information and give us even better sense of what the prediction should be.
Thanks, Victor. Yeah, I think that was a really comprehensive answer. I think both your answer and George's on different axes in some sense. And I kind of just wanted to understand a little bit, behind the kind of advantages and primary use cases you see for GNNs. We just talked about how there's different types of machine learning methods, some traditional, and the context of how GNNs differ from these methods. But I'm really interested in kind of hearing about some recommendations or advice that you'd have on using them as opposed to those other machine learning models. And maybe some of this a little bit more practically motivated by any success stories that you've seen with customers or folks that you've seen adopt graph neural networks, as opposed to these kind of standard historical paradigms. Just curious to hear if any experiences you have with those. Maybe Vikram might be a great person to chime in here. Vikram, I'm curious if any of the customers that you work with actually have this kind of problem that you deal with.
Sorry, I just want to cut this. I haven't prepared for that question. Sorry.
Oh, okay.
Can we just clip? Sorry.
Sure. Yeah, I can pivot to George or Victor. Curious if either of you have heard this.
Oh.
Sure. Let me get, I mean, actually, Victor kind of already alluded to one of the applications, right? I mean, recommender systems, right? I mean, people have been, have used, GNNs, for recommender system applications, extensively. I think, one of the early commercial success stories of graph neural networks, right, was in the context of actually a recommender system at Pinterest, right? Which, that showed to actually achieve much better result than the system that people were developing at that point in time. Now, but I'm going to look at another domain that people have shown GNNs to work extremely well, and that has to do with in the space of small molecule drug discovery as well as large molecule drug discovery, right? And this is for those who are not familiar, right? So one of the fundamental problems in drug discovery is that of given a particular chemical compound, right? You like to be able to predict whether or not it will bind or not to a particular protein, right? And then also for that particular chemical compound, what you want to do is you want to predict certain physical chemical properties, right? I mean, there's a set of properties that every good drug should have, like for instance, it can be absorbed, it can be metabolized, it should not be toxic, and a bunch of other things, right? So it's and people in drug discovery field, right? So the people in the field called cheminformatics, right, have been applying machine learning models, right, to solve those problems for the last 20, 30 years, for a long period of time. And chemical compounds are actually small graphs, right? Small molecule chemical compounds, are graphs, right? They have different types of nodes, which has to do with the different atom types, and then different types of edges has to do with the type of types of bonds that exist between the atoms, right? And graph neural networks have been deployed in computing representation of those chemical compounds, right, for solving either the physical chemical property prediction, or being able to do which was a regression problem, or being able to do a binary problem like bind versus no bind, right? Very successfully in the last 2 to 3 years, right? And the same thing happens also for more kind of a macromolecule kind of small peptide kind of drugs, right? So they can be modeled via graphs, and I can use those graphs to actually model them using GNNs, right? Within that space, actually, another exciting area of use of GNNs is not just to actually predict whether or not a particular compound would bind or not, but actually to generate new compounds, right? That by design, right, they will have a high binding affinity, right, against particular protein target, right? So this is the case in which GNN models are used in a generative mode, right, in which you generate compounds, right? And I consider to be actually a very exciting success stories of GNNs, right? Because number one, it's a tough problem, right? It's a problem in which any advances that we make in terms of shortening the amount of time it takes to design new drugs, right? That has some significant positive societal impact, right? And it's also an area in which for those who are familiar with the whole new era towards pre-training models, right? And we're familiar with those things in the context of like a language models, right? So you can leverage similar kind of pre-training techniques in the context of GNNs. And I'll let Victor add some of his favorite applications as well.
I think that was an awesome example, and I think we can also see the importance of finding new drugs and the effective new drugs more quickly as there was the race to find vaccines for COVID-19, and techniques like this were key to the speed at which that was achieved. Another area where we've seen, first of all, a lot of success, a lot of real world success for graph analytics in general, and is fraud detection and GNNs. And I would also add to that, graph embeddings have been a successful technique for, incremental increase in the accuracy of a model. And in the case of fraud detection, as in the case of recommendation, sometimes just a small increase can mean a lot to the organization that's using it. You know, catching 2% more fraud might mean millions of dollars. You know, or again, to a very large company, you know, making product recommendations that are successful 2% more of the time can, again, mean millions of dollars. Whereas, you know, we've actually seen, we've had customers report to us, they've even seen like 10 or sometimes more % increase, lift, so to speak, in the model. And again, that's because they're adding more dimensionality to the model, and that's always a trick where adding more dimensionality can make it computationally harder. So finding the balance between considering more variables and yet bounding the problem in a nice, like converging to a solution in a reasonable amount of time. But the graph dimensions, looking at the relationships, gives you in some case can better model what's actually happening. Like in the case of fraud, there's often, you can map out the pattern of how, if you knew how the fraud took place, you could sketch it out in a little graph pattern. The problem is they don't always know what they're looking for. So deep learning techniques enable you to find patterns using so-called latent variables, where you don't actually know what the variables are in advance, and you let the system figure them out just through the process of training, which is in also a way of like trial and correction to get closer and closer to something that works. You know, you know, there are cases that just doesn't mean that this is the golden answer. In cases where you do understand the dynamics, it may be more efficient to do targeted searches rather than using deep learning. But when the process is complex, as in chemical processes, you know, what molecules are going to form stably and interact with each other in the right way, it's a very complex problem. Techniques like this can be very successful.
Thanks once again for the super comprehensive answers. So I just want to pivot a little bit here. You know, folks who work on graph deep learning kind of know that DGL, or the Deep Graph Library, you know, it's a really key piece of software around supporting open academic research and development in the area of graph deep learning. So George, I was wondering if you could tell us a little bit more about DGL, you know, specifically like why was the project started and what was its mission, and maybe a little bit about how it's evolved over time.
Sure, I'll be happy to. So DGL, so DGL started about close to 4 years ago now. So this is an effort that started at AWS lab in Shanghai, and it's a framework for developing and training graph neural network models. Right? So that was something that was what prompted us to start that effort, right? But the fact that at that point in time, which was about 4 years ago, right, the frameworks that were available, right, for deep learning models were designed entirely for models in which the input data, right, was either in the form of 1D, 2D, or 3D arrays, right? So essentially, like dense tensor input data, right? And graphs, on the other hand, do not fit into that mold, right? So graphs, by their nature, they are irregular, right? The sparsity structure for every node is different, right? The number of nodes that each node is connected to is different, right? And the computation that involved, right, in actually training graph neural network based models are more of the type of like a sparse metrics by a dense metrics type of computation, right? And this type of computation was not really supported by the deep learning frameworks, right? So and in order for someone to be able to actually take advantage of the optimization that the deep learning frameworks of that time, were providing, they had to write their computation in the form of tensor operations, right? And if the graph is sparse, I cannot really do that, right? So what prompted, the effort in developing DGL is to make it easy for people to express the computations involved in graph neural networks, right? While at the same time being able to efficiently execute them, right, on the hardware of the time, right? And, even today's hardware, right? So both on, multi-core CPUs, so on the GPUs, right? And that was primarily because, the tensor-based API, so the standard deep learning framework, is simply not suited to express sparse computations. Right, so that was one of the things that kind of were prompting the design, and over a year, what DGL ended up evolving to actually provide a easy-to-use API in which kind of focusing entirely on the graph nature of the computation. So one of the paradigms, probably the most commonly used paradigm to write your GNN models is what's called the message passing paradigm. So the idea of the message passing paradigm is that nodes send message to their neighbors, right? And then the neighbors collect all the messages that they received. Every node collects all the messages they receive from their neighbors, right? They combine them and they use them to update the representation of the node itself, right? So what DGLs allow a model developer is to express the computation in the form of those message passing and aggregation functions, right? And it does all the heavy lifting in terms of taking those functions and executing them and efficiently on the underlying hardware. Right. So this is what DGL kind of problem the development of DGL, and over the years the development has expanded to support significantly more complex graphs. For about 2 years ago, we introduced support for heterogeneous graphs, also to provide support to allow for training for very large graphs in which there's not enough memory to put everything into a GPU, by providing mini sampling approaches, mini batch approaches, and sampling approaches. And recently we have been focusing on supporting training on extremely large graph by leveraging the distributed computing, right? Kind of approaches, right? So it's really kind of lower the effort required, right, to express the irregular nature of the computations involved in GNNs in a way that you get very good performance and also can scale to very large problems.
Thanks, George. And just a short follow-up here, given the context of the previous discussion on other types of graph embedding methods and other types of graph deep learning methods in general. Does DGL kind of support kind of the broad spectrum of traditional graph-based deep learning, or is it primarily support for GNNs, and do practitioners kind of need to look elsewhere for these other types of methods?
Yeah, I think to a large extent, the machine learning approaches that DGL supports are based on graph neural networks. I mean, a graph neural network is a very expressive, especially the message passing paradigm is, very expressive, right? So you can, and I mentioned that one of the advantages of GNNs is a nonlinear componentry. Well, you can choose a thing, or you can choose to use nonlinearity or not to choose to use nonlinearity, right? I mean, I can use, DGL and its message passing, paradigm to implement things like, some of the graph analytics algorithms, like, for instance, I can do PageRank, using DGL, right? And also I can use, a very shallow GNN model to essentially end up having a non-graph ML-based model, right? So by entirely building a model entirely based on the nodes features, right? So it supports a larger set of models than just GNNs, right? But it's optimized though for GNN-based models.
Got it. Thanks. And maybe even a shorter follow-up on this. Can you talk a little bit about how DGL compares to some of the other frameworks that are out there for graph deep learning, for example, like PyTorch Geometric or TFGNN that just recently came out from Google?
Yeah. I mean, at the high level, right? So DGL, PyTorch, geometric, TFGNN. I mean, all three of them are trying to solve the same problem, right? So, and the problem is that of making it easy for people to express, the computation associated with graph neural network, and then, take that computation expressed in a Python, code and execute it efficiently on the underlying hardware. Right. So some of the key differences I would say between DGL and PyTorch geometric and TFGNN is that so DGL on from the get-go was designed to be a multi-platform library, meaning that it will support it support both PyTorch, it support both MXNet, actually both PyTorch, MXNet, and TensorFlow, right? So and the idea there is kind of, we are very agnostic on what is the underlying framework, right? In order to achieve that, what DGL ends up doing is incorporating providing a high level or a larger number of APIs, right? So that it will kind of abstract out the underlying framework as much as possible, so that people will be able to, when they move from a PyTorch to MXNet or to a TensorFlow implementation of the DGL model, will minimize the amount of code change that I may have to do in order to actually go from here and there. Right, so that was one of the things that differentiate DGLs, versus PyTorch geometric that is entirely geared towards PyTorch, or TensorFlow GNN, which is TFGNN, right? And then the other part is one of the kind of the team has spent a lot of time optimizing for performance, so that was pretty much from day one, and scalability, right? So and it really is designed to to achieve a high computational efficiency on single and multiple GPUs, and also being able to do that thing in a distributed setting. So if I'm going to look at scaling those frameworks to larger and larger graphs, I believe DGL is probably the most scalable framework at this point in time.
Got it. Thanks, Serge. Yeah, I guess a quick follow-up in addition to this. I know I have a lot of quick follow-ups, but there's a lot of interesting stuff about DGL out there. So really excited to kind of have you here and shed some light on it. But in case you can share any secrets with us about some of the exciting upcoming developments for DGL that you're particularly excited about, that are maybe not supported yet, but are in the works. Do you have anything you can share?
Sure. I mean, there are actually there are three directions that we kind of putting a lot of effort in DGL, and by the way, one of the things I would like to comment over here, I mean, DGL, even though it's it was initially created by the AWS on one of our lablets, it's really an open source effort, right? So we have a lot of people actually contributing on DGL, right? So when I'm going to say some of the stuff that's on our roadmap, right, or stuff we're working on, it's the royal we, right? It's essentially the community is working to tackle those problems, right? So one of the things that we're working on, and I think I think it's very exciting, it's something that I think it's pretty well known in the community, right? So in order to support, to make something user friendly, you provide the ability for someone to provide you a user-defined function to do certain things, right? But the problem with the user-defined functions is that then you have to take that thing and then actually kind of support it in some sort of pretty much an interpretive way, right? So you don't get as high of a performance as taking that UDF, right, and implementing as a built-in, right? So that's why DGL provides a lot of built-in operators, right, that they're specifically designed for some of the common use cases, right? Plus it provides the ability for someone to provide a UDF. Right, but there's a performance gap between what I get from a built-in versus UDF, right? So one of the things that we have been working the last year or so is actually on a compiler technology, right? That will take those UDFs, right, and actually compile it, right, and in a way that will actually achieve performance that is comparable, right, if not better than you get from a built-in, right? And this is something that some of the the advances we have done on that front, right? And we're available in the 0.8 release of DGL that was made available a couple months ago, right? But this is something that we continue to work on, and we hope to be able to to bring more of the compiler technology we've been developing into DGL, right? So that's one area that I think I'm looking forward to seeing the performance gains. The second area is one of the things that we realize is that I think sometimes our API is not necessarily very intuitive. So we're actually in the process of actually doing some API redesign, to make it more user friendly. And then the third part is something that we started almost 2 years ago, and the whole journey of distributed training, right? For very large graph GNN models, right? And I think I believe we have done a very good job in addressing the core aspect of training, but there are some things that has to do with both the data pre-processing side of things as well as the inference side of things, right? That need to be addressed, right? In order to actually be able to actually develop a truly scalable and easy to use end-to-end solution for large GNN training, right? So one of the things that we're working on is how to speed up and optimize our data pre-processing pipeline, which to a large extent we assume that the graph will automatically appear, but I'm sure Victor will love to do that, but sometimes the graph does not automatically appear, right? And then the second part is when it comes down to actually doing an inference, or even if you do like a validation stuff in the context of a very large distributed training, that becomes a challenge, right? And and what we're working on is to develop the extend distributed DGL to allow to do that.
Thanks. Yeah, I think those advancements sound really exciting. Speaking as someone in the industry who would love to make use of these kinds of data preprocessing and inference pipelines, for sure. So yeah, I want to change gears a little bit and talk a little bit about how something like DGL kind of fits into product strategy. And maybe I kind of want to hear both answers from the Amazon as well as the TigerGraph side. So I think maybe Vikram and Victor, you guys may have some thoughts on this.
Sure. So understanding these benefits of what George has just talked about regarding DGL, we have built a SageMaker support for DGL. And what does this support do is like, it removes the burden of packaging the software dependencies and building infrastructure and finding the validated model. So as a result, you can implement, test and implement your GNN models in hours rather than normally it takes like weeks or months generally, right? So with this support, you can do it in hours. And you don't have to worry about scaling your infrastructure while you're training your graphs, because AWS takes care of scaling up and scaling down of the infrastructure. So you can completely focus on building your use cases and training your graphs. And with this, you can immediately test your GNN models and integrate with your applications dynamically.
Okay, that's great. I can add to that what this means to TigerGraph. So for TigerGraph, our customers have seen the value of using graph analytics for answering their business needs. Originally, that was through queries and graph algorithms like PageRank, like community detection. But really, the path of taking a graph, maybe extracting some graph features, you could be use case specific, could be again general purpose like PageRank, thinking of that as a node feature. And now I've extended the feature vectors. Now I know more about each feature. And then the traditional approach was, okay, now I've enriched my data, but I'm only going to look at the nodes now. And so I'm going to export that as a table as a matrix or tensor of node vectors and train on that. And so the use of graph as a rich source of data, feature engineering, and then doing machine learning was established. Then along comes graph neural networks, and we said, hold on, we can do even better integration. And so we've been working on this closer integration. So with the rise of DGL and other similar libraries, our goal at Tiger Graph has been to make it as easy as possible for data scientists to take advantage of the potential. The number of people who know Graph and the number is small compared to the number of people who call themselves, working data scientists and machine learning engineers. So there are more data scientists out there. So we said, look, we're going to come to you. We're going to make our work environment look like the environment you're used to. You want to use DGL? Great. We're going to make a Tiger Graph Python library so you can, manipulate the data, export the data, do the subgraph sampling that George referred to, do, graph data partitioning because you want to do data partitioning. We're going to make that easy, but it's all going to work with DGL or PyG. And so again, our job was where we think what actually makes business sense for us is not to try to, pull people in the direction we want, but to go with the flow. The flow is towards things like DGL. And so, we also have integrated with SageMaker. So AWS was the first cloud platform that Tiger Graph ran on. We still see the most business there. And so we see this as just another great addition to the toolkit that data scientists now have. One more thing I have to say is that when George was describing some of the characteristics of DGL and what makes it special, he mentioned message passing and distributed computation. And those are two things that are also very much in the DNA of Tiger Graph, message passing and distributed computation. So right now, our mode of using DGL is still to export the data from Tiger Graph, but the door is open for us to actually implement it natively within our database. Obviously we've got to solve some of that. How do you optimize the efficiency of the compute operations? Because the database, just like he mentioned, work had to be done to deal with the non-tensor nature of graphs. We've got a graph, but we don't have a tensor engine right now. So, how do you marry the two? That's a challenge that we're looking forward to at Tiger Graph.
That's awesome. Super exciting answers from both of you. And just wrapping up a little bit, like you said, Victor, there's a far larger number of machine learning engineers and data scientists who work in the broader domain than those who actually work in the graph domain. And so I kind of just want to open this question up to the floor and roundtable it a little bit. But what is kind of one piece of practical advice that you'd give to someone who's starting out in the graph learning space? I'm sure that each of you have different perspectives on the type of folks that you work with and what that initial starting point that people are coming in with is. But either way you want to interpret this question, I'm really interested in hearing something that all these folks, machine learning engineers and data scientists who are listening to this can start doing to practically kind of build their knowledge in the space.
I can take a crack.
Go ahead.
Someone else can contribute afterwards. So Neil, this is a very good question, right? But now, if you had asked me that question 3 years ago, I said, man, there's not a lot of information out there. You have to start, pretty much from scratch, right? But right now, there's a lot of information out there, right? So people can learn about graph neural networks, right? And the way I will tell people to how easy to tell people to start is number one is kind of the whole kind of crawl, walk, run kind of approach, right? So you it's always a good idea to read some of the initial papers in that field, because that'll give you some sort of theoretical kind of foundation, right? You don't necessarily need to understand every single math equation that exists over there, but at least be able to understand what is the intuition, right? And under what conditions you expect these type of approaches to work, and what are the conditions which those approaches can potentially run into issues, right? So it's just it's a good thing to have at least some sort of some understanding about what you use, right? But then after that, what we'll do is, pick up, your framework of your choice, right? DGL will be my recommendation, but I'm an open person. So and then start by looking at look at the tutorials that exist on GNNs. Look at some example model that someone else has implemented, and and those things are available within the frameworks, right? And start running some experiments and seeing what works, and see how it fails, right? And start modifying it, and and kind of slowly building expertise in that area, right? And but the good thing, as I mentioned, there's a lot of content out there nowadays, and that can help you get started in your journey.
I will just add a few things about how you can run DGL on AWS. Is like we have developed various one-click deployment solutions, like, for example, real-time fraud detection using GNN on DGL. So it's like we have completely scripted everything, all the infrastructure as well as application configuration. With just one click, you can deploy it on AWS Cloud. And right now it is available in all the AWS global region as well as in China region as well. So I would suggest viewers to try that solution, which comes with end-to-end demo of how it simulates the financial fraud detection. It builds up all the heterogeneous graphs and trains the GNN model in the real-time fraud detection. And it also gives you a dashboard where hundreds and thousands of online transactions are generated automatically, and suspicious transactions are detected, and all of those is working in place. So I would suggest, if the viewers want to try it and want to see how it is working in real time, they can just use our one-click deployment solution. And there are many Python notebooks available on AWS documentation about DGL, so feel free to use that as well.
So Tiger Graph is in, our business is graph, and so we're always trying to invite people to consider using a graph. The thing about a GNN is you have to have a graph first, right? So do you already have graph data? If you already do, then as George mentioned, there's a lot of tutorial resources, as Vikram mentioned. They've got the support. I think they're making it very easy to try it. If you don't yet have a graph, then you have to think about, well, do I have a potential problem where or task where forming my data, representing it as a graph would give me some advantage. And we see, again, sort of a spectrum where you don't have to be going to the state-of-the-art GNNs. It could be just you want to make a knowledge graph, and I use a so-called small k. Doesn't mean that you're going to follow the RDF semantic graph standard necessarily, but you just want to represent what you know as a graph and ask queries, or you've heard that certain graph algorithms are useful. And you can take the steps in that way of, I'm going to try some graph queries, I'm going to try some algorithms. Now I'm going to move into, machine learning with some graph features, which will, and I can still use my traditional neural networks, or I can use k-nearest neighbor or random forest. But again, I would not be afraid to try GNNs, because I think it's now very easy to do so. But if you don't yet have a graph, then you're going to want to kind of look to some of the examples of some of the use cases you might be interested in, and how have people designed their graph, because you got to have the data first. But it's not hard. And there, just like there are GNN examples out there, there are graph data structure examples out there.
Thank you all. And finally, just as a last catch-all, is there anything that anyone would like the audience to know that we haven't covered just yet? Anything you didn't get a chance to share?
I think we've said it, but I just want to reiterate that DGL is an open source project. And so it's it's available for anyone to try for free. I really am so excited that AWS and you know, prominent researchers like George have been involved to deliver this to the you know, the scientific community. So it's just out there for anyone to try, and so give it a shot. And you know, if it works for you some of the time, that's a win.
So I will continue on Victor's kind of, you know, line of thinking, right? So not only, you know, give it a try, but also you're more than welcome to contribute to it as well. So so if you go to the DGL's website, right, you'll find a lot of information in terms of, you know, how to contribute to the effort. You know, there's a Slack channel that you guys can join, right? You know, and actually can use that thing to ask questions, right? And then I'm going to wear my hat as a professional, and I will say that I think, you know, the field of GNNs, right, is a very exciting, you know, research field, right? And if you're thinking, you know, what to be focusing in the next, you know, K years, where K is greater than 1 and probably less than, I don't know, but pick a number. So I mean, this is definitely a field. It's an exciting area of research, right? There are a lot of, you know, it's very active field. You know, people are exploring, you know, every day, you know, new applications of GNNs, right? And just to give you an example about the whole GNN, and again, you know, most of the people who work in that field know that, right? You know, probably the most popular, you know, deep learning model nowadays, which is a transformer, right? It's actually a GNN. It just happens to be a very boring GNN. That is, you know, everything is connected to everything, right? But that also gives you kind of an idea in terms of, you know, one way of potentially improving upon transformers, right, is by introducing some priors, right, about, you know, which connections are important and which connections are not important, right, by imposing a sparse, you know, graph structure on it, right, and that can also reduce the amount of time it takes to train those things, right, and also give you, you know, better results.
Thanks, guys. Okay, so thanks, everyone. This was a really amazing discussion. I really appreciate the panelists' time and friendliness and sharing some super deep domain knowledge in fairly different areas. And I really hope the audience got a lot of value from this as well. And I just want to add my own personal endorsement. You know, I've been in this space for several years, and you know, and the academic and industrial research and development in this space continues to be like massively interesting and impactful. You know, you don't have to take it from me. You can also take it from these guys. You know, there's a lot of support and encouragement to work in this area. And if you're in the audience and you want to get started in graphs, please don't be discouraged. Please take everyone's advice here. You will not regret it. There's a lot of value to be had in the space. Thanks again.
Thank you.
Thank you.
Good.